First two sections of chapter one are an introduction to electrical circuitry. And beginning with page 3 of the workbook, let's start off talking about current. And so in electrical circuit, charges flow through conductors, typically wires, connecting wires that conduct electricity. And these wires are connected to various sources, voltage sources, which create forces that cause the charge to flow through the conductors, the wires, and other circuit elements. Illustrated here in figure 1 is a very common typical circuit that we will see later on in the course, which has a variety of different circuit elements. I thought I'd just go through right now just to give you an illustration of what these different symbols represented in the circuit represent. Circles, like this on the left here, with the polarities plus and minus, that typically is a voltage source, which might be a battery, or it could be supply power from any particular type of transformer. In the top examples, these lightning bolt type of elements here, those are resistances. Again, from previous physics courses or engineering courses, fundamental courses you've had, you might be familiar with these. The coil here, that's an inductance. And this final one here with the two parallel bars there, that's an example of what's called a capacitance. And again, we will certainly cover each of these circuit elements in this course, but for now, we're just illustrating the variety that we might have in a typical circuit. What's important right now is the idea of what we mean by current. So an electrical current is a rate of flow of charge. So that's important to realize that current is a rate, and it's the rate of flow of a charge through the conductor, as well as a circuit element. The unit for this rate is given by amperes, capital A, and the rate is specified by, again, charge per time, and the measure of charge is in coulombs. And usually, typically, that's represented by a capital C. And then because it's a rate, we say coulombs per second, or the little s indicates seconds. The charge on a single electron, we know, is negative 1.602 times 10 to the minus 19 coulombs. So one question is, how does one determine or measure current? So we'll just do a little diagram here, sort of blowing up what a conducting wire might look like. If we blew it up a little bit, we could draw a three-dimensional wire. So we'll just do the best we can with some sort of a three-dimensional kind of drawing here. But what we're really looking for is a cross-section. And we'll take maybe the cross-section here in the middle. So this is an illustration of a cross-section of your conductor. Again, we are illustrating current through a conductor. And what's important is that we have a flow. In other words, we have a reference direction. And this arrow here indicates the direction of the flow of the charge. So this is called the reference direction. In this case, it's left to right. So when we record the net charge through a cross section, so we're looking at how the net charge is changing through a cross section of a conductor. We use plus or minus to indicate one of two scenarios. One scenario is that a positive contribution to the charge is denoted by a plus charge in the direction in the reference direction. A minus charge is against, all right? So when we choose a reference direction and we measure and have a positive value for that current, what that's saying is that, in fact, we're getting a positive contribution in that direction. If we measured and get a negative value back, let's say and we chose the reference direction, say left to right, what that would mean is that, in fact, the rate of change, the flow is going from right back to left. So it's just plus or minus is an indication of, are we following or not following the reference direction? Similarly, you can say that a negative contribution of a net charge is represented by a plus if you're going against the reference direction, or a minus charge in the reference direction. Okay, but I think if you, we'll see some examples to clear this up if there's any confusion. But again, we choose a reference direction, and then whether or not we measure a plus or minus is indication of was that the correct direction of flow. In terms of the value of current, if we record the net charge in coulombs as a function of time, because many times current is not constant, it will change with time. So we typically represent charge by Q, little q, and so as a function of time, it would be a function Q of t. So fundamentally, current is simply the rate of change, and we know from calculus another way of the instantaneous rate of change could be represented by a derivative. So current, in this case, is indicated by lowercase letter I, as a function of time would be I of t, and it's simply the first derivative of that charge function. So we could also write I of t is equal to Q prime of t, again, using the same kind of notation you're familiar with in calculus. A constant current of 1 amp, for example, which would be 1 coulomb of charge passing through that cross section, which we just drew each second, all right, would certainly mean that it's not changing with time, all right. But it is important to know that you can always go from one value to another. In other words, if you knew what the current was and you needed to understand how much charge had been flowing through that time, then what you could do is use the fundamental theorem of calculus here and say, well, if current is the derivative Q, then to get Q, we would integrate the current function. And that's illustrated here by this particular derivative. We'd have to have a reference point in terms of the initial time. And so that would be represented by T0. And we would integrate from T0 up to an arbitrary position T in time of I of t dt plus the initial charge that we started with, right? So again, that's just basically applying the fundamental theorem of calculus. So, and again, T0 is the initial time for which the charge is known. So again, current flow is the same across all cross sections. So when we go back to the figure, what we're saying is that it didn't really matter where the cross section was taken here. The current value would be the same regardless of where the cross section was. It's uniform, okay? Albeit no material property variations through the conductor, which sometimes is a concern. So as an example, let's look at a charge function that has two parts, okay? And notice it's illustrated in the notes here at the bottom of page 3 in two different ways. Indicated for time less than 0, which just means initially, before anything, a switch is fired or power supplied to the circuit, we have no charge. And then instantaneously, and that's why it says from t greater than 0. Rather than saying there's no equal 0, it just means instantaneously when there is charge, that it will become an exponentially based function of this force, 2 minus 2 e to the minus 100 t coulombs, all right? And again, another way to realize that it's 2 minus 2 times 1 over e to the 100 t. So keep in mind the meaning of the negative exponent here, all right? So what we'd like to do is to draw the current and the charge function through time, just to sort of illustrate the behaviors of how current values increase or decrease relative to the charge flow, right? So let's flip it over to page 4 and look at this box here at the top here. And we are looking at this particular function. Again, I'll redraw it here at the top here, just so that we have it available. So that Q of t is initially 0. Again, we note that as time less than 0. And then instantaneously it becomes this function when power is supplied or a switch is opened. It's 2 minus 2 quantity e to the negative 100 t coulombs, and that again is for past time 0, okay? So by definition, we know that current is nothing but the derivative. So we will take the derivative of your charge function with respect to time. And of course, the derivative of 0 is nothing but 0, so nothing changes initially. But if you use your Calc 1 rules on the derivative e to the u is e to the u du, then you should be able to determine, first of all, the derivative to the 0. And we have a minus 2 constant here, but we're going to pull that negative 100 down when we take the derivative, and you should get 200 times e to the minus 100 t. And now this will be in amperes, okay? And this is for time greater than 0. So just a very simple sketch, nothing super exact here. We're just trying to get trends here. So I'm not going to need to make a table here to produce some values. But let's suppose I use this border here, and I'm going to draw the charge function in coulombs. So that's the Coulomb axis. This is time, and let's suppose we do time in milliseconds, okay? And again, a millisecond, of course, is 10 to the minus seconds. So the scale here is really tiny, so to speak. And that's because the size of the values we're getting relative to an exponential raised to negative 100 t power, all right? So if we block out these milliseconds, starting with 0 in increments of 10, we'll go up to 40. Because as indicated in the box, we only wanted to go up to 40 milliseconds. Of course, initially we know there are no coulombs, so you have 0 there. And you can see in the limit, if you take the limit of this function as time goes to infinity, this component right here is basically going to become annihilated. It's going to go to 0. So it doesn't take long to realize the steady state, or in other words, what the charge function is eventually going to asymptotically converge to is 2, correct? Because again, this term will go to 0. So what we can do is just sort of sketch in just sort of eventually what's happening. And again, just the shape of the curvature is fine to say, look, eventually it's going to hit 2 at some point, and that's going to be staying underneath 2. Okay, it'll eventually become closer and closer to 2, but because you're going to be subtracting a tiny amount from 2, it'll never quite get there, right? Because again, no exponential will ever produce the value 0, all right? But it'll just be a very, very, very small value that's going to be subtracted. Okay. If you, on the right here, were to sketch the current function, which we'll do, keep in mind you want to keep your time scales for all our graphs the same, so there's no confusion in comparing. Otherwise, it'd be very difficult to eyeball the comparison. So we'll keep the time scale the same in milliseconds. And here what we're drawing is the current function. Okay, and again, this is amperes, right? So this is now determined by the value of the derivative up here. And again, the difference here though is current, when time is greater than just past 0, we know we're going to be essentially at 200. So what we'll do here is, again, we'll mark 200 here. And since initially it's not there, maybe we'll leave an open circle there. Just sort of illustrative, you know, we again, right at time 0, there's no current, but just past it, it's going to be there. But what will happen here clearly is this will excuse me, right here's where we are. Asymptotically, it's going to be dropping, right? And it's going to be dropping to 0. So it'll get closer and closer to 0. It'll never be exactly 0 because again, no exponential function can ever produce an you know, think of logarithms there, it cannot be exactly 0, but it'll get very, very, very close to 0, even though it's scaled by 200, okay? All right, so that's what the important trend here is to realize the minute the charge flow stops changing, your current is going to 0. So current is always about the rate of change of the flow, all right? So initially, it's very high because this rate of change is very high. And then as this slows down, this stops, okay? So that's important. Let's talk about assigning reference directions. Many times we don't know the actual direction of current flow, and so we'll just go ahead and assign a reference direction, okay? So here's an illustration in this figure 2, circuit 2, where we have 5 different circuit elements, and we've indicated arrows here, a current here I1 coming into B, leaving A and coming into B. We have a current I2 coming in, coming downward through C, and we have a current, say, coming from top to bottom through E. So arrows are indicating the reference directions here, okay? All right, but what we're illustrating here, these were reference directions chosen, but if we in fact were to measure and obtain this value, minus 2 amps, from a measurement of the current coming, let's say, flowing through A there, and our reference direction was indicating this direction, the fact that this value is negative, what that really tells us that is actually 2 amps are flowing from top to bottom, that the reference direction is not indicating of the correct flow. All right, so the value is correct. We know it's 2 amps, but the actual current is flowing downward. okay, all right, relative to the reference direction, okay? If this value had been positive 2a here, right, then what we're saying is, okay, it is in fact flowing from bottom to top, okay? So that's the meaning. The plus value says, yes, the reference direction is in sync, or it's not, okay? So, of course, if current is constant, if we look at the bottom of page 4, if current is constant with time, all right, that's typically what we would have in the case of a voltage source being a battery, and that's what's going to happen with the direct current. Alternating current, however, is the case for which your current is actually changing value and polarity. It actually changes directions, so to speak. So it can actually change periodically. All right. And so I thought we'd illustrate that just by a couple of graphs here, just some illustrations and then some examples following on page 5. So if we go to page 5, in the first box, at the top of page 5, we'll just draw two cases of current. We'll draw a typical DC current. And again, for many of you, this is probably review, which the first chapter of the workbook pretty much is, but it's good to make sure we're all on the same page and we're following very carefully the same type of descriptions. So an example of direct current would be a constant current. So let's let time be seconds, okay? And again, the vertical axis or proverbial y-axis here is amperes, okay? And of course, if the function was a constant, it would not matter what time is. You would have the same current value. And so 1 ampere, 2 ampere, nothing changes. So that even at time 0, it's always 2. So that's a constant current there. AC current, however, is very different. In this case, it can change signs, SIGNs, and magnitudes. So we're going to draw the graphs slightly different here, using both sides of the y-axis here. And again, we'll let time be seconds, and we are measuring amperes. But let's suppose we come up to 2 and can drop to -2, right? And maybe we'll indicate, let's say this is a half second, and this is a full second in time. And what we'll illustrate here is that we will have inflections through this the x-axis or the horizontal axis in this way, so that maybe the current is positive and then drops negative and drops to the same value. So maybe we'll sort of illustrate that typically you will have a very trigonometric kind of behavior here, sine or cosine. In this case, it looks like more of a cosine curve because at time 0, we're up at 2, not at 0. So this is typically an indication of what you might have if you were to have an alternating current versus a direct current, right? And we will look at cases down the road of situations like that, right? So, and if you wanted to get an illustration of what this equation for such a current might look like, this is an illustration of something of 2 times cosine of 2 pi t, okay? So that's an illustration of an alternating current. Very different behaviors. You could also have waveforms that look like this. You could have a triangular type of waveform. Again, magnitude and polarity is changing, but this is not any sort of a sine or cosine function. Very harsh kinds of abrupt changes. Even worse than that, you could have something like this, a square waveform where the current is being held up. It's being held and dropped and held and dropped, very suddenly through time, right? Reference directions can also be, you can specify them in the circuit by arrows, but you can also use indexing by the terminals associated with the circuit element, okay? And that's what we're going to illustrate next. If we go on to page 6, we have resistances here. We have 2 resistances, and notice that they're basically the same in terms of the terminal. The top terminal is labeled A and the bottom terminal is B. Notice that the arrow of direction, and this is to indicate current reference direction, is from A to B for the one on the left, but it's from B to A on the right. Didn't matter whether the arrow is at the bottom or the top, it's the direction of the arrow that matters. But this illustration on the left is another way of writing it without an arrow. If I index the current as IAB, I'm referencing the direction from A to B. So the first subscript is where you start, the second is where you end, or where it's flowing out of. So again, this first one on the left is an illustration of current indexed IAB. The first subscript is where you start, and the second one is where you stop, so to speak. The one over here on the right is an index of current IBA. In other words, you start at B and go through A. So again, goes from the bottom to the top. So that can be very helpful sometimes. In the case of designs where you don't want to have a lot of arrows, just index the current this way, right? A couple of examples before we end the lecture here, just to make sure we have the understanding we need here, is let's just look at a simple example or two values. First of all, if you had a constant current of 2 amps flowing through a circuit element, a current element, and in 10 seconds, how much net charge would pass through it? All we're doing here is just making sure we understand that, of course, current is a rate. It is always coulombs per second. And here, if we know that the constant current is 2, and that you're interested in that it occurred in 10 seconds, it was constant, how many coulombs passed through there, then it's quickly to see that must be 20 coulombs, again, because 20 divided by 10 would be 2, all right? So again, it may be a function of time, but if it's constant, it's just that simple ratio. Let's suppose that in example 3, you have a charge that passes through a circuit element, but now the charge is changing. In this case, it changes by sign and magnitude according to a sign function. And we ask, what is the current as a function of time? Again, we know it is a derivative, the first derivative of your charge function with respect to time. So you're taking derivative of this function here. The constant, you pull it out just like you did in Calc 1, and you're taking the derivative of sine 200t, which should be 200 times derivative of sine is cosine, so we should have cosine of 200t. That's the angle, and that is amperes. Again, you multiply these two, that's 1 over 100 times 200 is just going to give you 2 times cosine with an angle 200t amperes, right? So what's interesting here is that if you were to think of drawing, you have a sine function here representing your charge flow, but your current is shifted and adjusted by a cosine. Same angles though, okay? Finally, example 4, this is to make sure we have an understanding of reference directions. Let's assume that the current in the circuit below is defined as a positive charge, and we obtain the following measurements, okay? So again, here are the reference directions. The current through A goes from bottom to top, the current through C goes from top to bottom, and the current through element E is from top to bottom, again, looking at the direction of the arrows. But let's say that we have these measurements, that it turns out I2 is 1 amp, and it turns out that I3 is -3 amps, right? What do we know? The question is, in which direction, upward or downward, is the charge moving through element C? The reference direction was top to bottom, and we have recorded a measure of 1 amp. So the fact that this is positive means, in fact, the reference direction is correct here, in the sense that certainly the current is flowing downward, okay? But then the reference direction was top to bottom, but we obtained a -3 amp value. In this case, what that says, if we're looking at a positive charge contribution, all right, but the current value is negative, which means that, nope, it must have been going from top to bottom. So in this case, it would be upward, right? So again, if the value here is positive, then the reference direction chosen is the actual flow direction of the current. If you get an opposite sign, in other words, minus this case, assuming that we're looking at a flow of a positive charge, which most times that's what we're going to do. Where it's just a standard to say, suppose the positive charge is the net charge we're looking at flowing through a current element. Then the fact that this negative means the reference direction is actually opposite from what it should be, okay? And that concludes the material for these first 2 sections.